All right, so this is lesson 4-3. Um, the lesson itself, I had this video created somewhere and YouTube didn't like it for whatever reason. It wouldn't upload it. So I am creating a second version of part 1 here. So bear with me if things sound repeated. I will do my best to try and replicate the first video. But as we get started, we are talking about vector fields. So the idea is with a vector field, rather than assuming, say, in 4-2, we assume that, if we had an airplane that left Waterloo and headed to Minneapolis, that the wind was consistently 45 miles an hour at exactly, I don't know, a heading of 80 degrees, whatever it was. But you could imagine that in the real world, in 3 dimensions, real life, the wind isn't going to be exactly that magnitude at exactly that direction for that entire 180 miles or however far it is. So in order to more closely relate that to the real world, we have what we call vector fields. So what a vector field does, as it says in here, and in vector calculus itself, which is its whole own semester-long class, but a vector field assigns a vector to every point in a subset. So that subset of space might just be negative 10 to 10 in the x, negative 10 to 10 in the y, and in the real world, negative 10 to 10 in the z. But the idea is that every point, over 1, up 1, or whatever it is, whatever point, that point has its own vector. That vector has a magnitude and a direction, and that magnitude and direction could very easily be different in direction or different in magnitude or both from the vector in point 1, 2 or 2, 3. So anyways, it says the vector field in the plane can be visualized as a collection of arrows. So, and you'll see that in the activity itself later on. In fact, maybe I'll take a second and scroll down. Here's a good example. So here's a collection of arrows in the field negative 10 to 10. And each one you can see has a little bit different angle, a little bit different magnitude based on how long the arrow is. So yeah, that's basically what vector fields are. They're used in a lot of different things to replicate space, fluids passing through space, or just all. I mean, it even does traffic patterns for studies of traffic on the highway. Anyways, here's how you do one, or here's how you create one. You evaluate the vector, as it says in step 1, at x comma y. So you start your vector at x, y, whatever point that is. And then you evaluate it in the vector field, which is an equation. So you have a starting point, x, y, you plug that into the equation, and it's kind of like getting a y value out of an equation from what you're used to in algebra. You have an x, y, you plug it in, and you get a result. Step 2 is you graph that with the original point, the initial point of the vector at x, y, and then from there you would go up and over or down and over, depending on what the vector field evaluated to. So, and then step 3, do it over again. So I'm going to demonstrate this as such. So the table that we drew in class looks something like this. So I'm going to try and replicate that. But here's your initial point, and these are those given points up along here. So 2, 1, negative 1, negative 1. And we're just going to skip to the last one, negative 3, 2. And when I learned these and went through vector calculus, we just had 2 columns in our table. But there was a teacher that, I guess Mrs. Gerber, but one of the 2 teachers showed me this table that she uses 3 columns. So I'll demonstrate with 3 columns. You do information what you want. But column 1 is your initial point. Column 2 is the evaluated f of x, y. So if we plug 2, 1 into the equation, our equation we're evaluating is right here. So the new x term of the output, like our output end point. So where does the endpoint end up going from 2, 1? Where do we go? The x term goes to a value of our original y term squared. So our original y term was 1, so we take 1 squared. So our new x term is just 1. The new y term of the endpoint of our vector uses our original x and subtracts 1. So we take the original x, which is 2. 2 minus 1 is 1. Now, in general, what this is saying is you start your initial point at 2, 1, so that's right here. From there, we go up 1 and over 1, so we go here. And there's our vector. Now, the third column, which for some of you might be kind of handy to see and do, but your terminal point is just going to be, if you take the x of this point and x of this point, you add them, you get 3. And same thing, 1 and 1, so you add your y terms and you get 2. So what this point is going to give you every time is where the end point of the arrow actually is. So this middle column is just telling you where you went from the initial point, but this third column tells you from the origin, I went over 3 up 2. So let's do that for another point, -1, -1. Our new x term uses the old y and squares it. So -1 squared gives us another 1. And our new y term uses the old x and subtracts 1. So -1 minus 1 is -2. So from our original point, you know what, I'm going to use red for this one. So -1, -1. We started here. And from -1, -1, we go over 1, down 2. So over 1, down 2. Okay, so that's what our vector looks like. And I'll even keep using red for this. So if we were to take -1 plus 1, that's 0. -1 plus -2 is -3. And what you find is the end point of our arrow was at 0, -3. So again, the third column, I've never used it, but I do see how it can be handy. But typically we just take our -3, let's switch to blue, -3, 2, so let's see, our y term, our original y squared, so that's 4. Original x, -3 minus 1, so -4. -3 and 4, that's 1. Excuse me, and then 2 minus 1, that's -2. So again, what I would do is I'd start at -3, 2, so -3 up 2. And from there, I'd go to the right 4, down 4, to the right 4, down 4. That's our vector, but we can confirm that that's right because we know that the terminal point of the vector is going to be at 1, -2, which is confirmed. So that's how we do those types of problems. And I believe that's all we did for part 1. So I'm going to stop there. I believe video part 2, which is already done and uploaded fine, that's already on YouTube. So there you go. That's how we evaluate vectors in a field. We don't analyze them, we actually evaluate. So there you go.